So now we're going to begin talking about class of meters. We're going to talk about class designations, service types and voltages, nameplate information and socket-based configurations, and also take a very close look at terminal markings on meters. So class designation of meters. There's two main categories of meters that we all are probably pretty familiar with, but self-contained class, these are the meters that house all of the measuring elements within under the cover of the meter. For example, the Form 2S meter that's on your house, we all know that that's a meter that is inserted into a socket that basically has the voltage and the current elements, all within the cover of that meter. And the classes of meters that we deal with on self-contained are 200 and class 320, and also a class 480, which is the K-base bolt-in meter that Landis+Gyr is the only manufacturer that had ever manufactured that. And so basically there's really nothing else required within a self-contained meter, to put that into an operational condition other than it being in a socket. So instrument rated class meters, these are meters that house measurement elements that are also connected to external devices that we know to be current transformers, and in some cases voltage transformers. And the classes of meters that we deal with there are predominantly class 20, even though Landis+Gyr still builds a class 10 device, but most utilities are not using a class 10 meter any longer because the engineering effort is designing the installation for full 20 amps of current. So class 20 is predominantly what we see here. So manufacturer uniformity. So many decades ago, when the electric utility business was really expanding, in the U.S., there were probably as many as a dozen different meter manufacturers that, were startup companies back in the early 1900s that were building meters, and they were engineering their meter to the specifications that they felt like a meter needed to be built to. And so there were a lot of different companies out there. And so there was a condition that kind of began to set itself up where the firms that were building these meters were building them to different specifications, and it began to be a little problematic. And so manufacturer uniformity became a more important thing as time went on. So we're going to talk about that a little bit. And ANSI requires manufacturers to conform to specific design criteria pertaining to electric revenue grade meters. And this was very helpful as time went forward because it didn't really matter who the manufacturer was. They would build their meters around the specification of ANSI so that nameplate information was more uniform, across the board. So that became a necessary thing. But we'll talk about these things a little bit more specifically in terms of base plate configurations, nameplate information, as well as socket configuration, class amps designation, also test amps for the accuracy testing, voltage ratings, which we're going to talk just a little bit more about that as compared to the old mechanical induction meters, cover options, and then basically the last thing we'll talk about is some communication protocols, since nowadays meters are not generally manufactured without some sort of communication that's built inside of the meter. So form types. So I've mentioned here several times in this training that you're developing a vocabulary for terminology, you're developing a visual association to information so that when that term or something is mentioned, then you immediately associate that. Well, form factors are another one of those things. Every meter that we deal with in the electric utility business has a form factor associated to it. So as you develop a memory of those form factors, there's a number of different things related to that come to mind, like transformer configuration, whether it's self-contained or instrument rated, whether it's a residential or maybe a commercial type installation. So we're going to go over these in three different groups. And the first group that you see here is relative to the residential class only. Obviously, we have our Form 2S Class 200 meter, which is, again, the most predominant meter in any utility. Class 2SE, you'll notice, is capitalized here, which is a designation for the Class 320 meter. And then the 2K, or the bolt-in meter, which is the Class 400. And then two instrument-rated form factors that are the equivalent to the self-contained. A Form 3S is an instrument-rated meter that's a 2-wire meter. It's equivalent to the 1S, which I didn't list the 1S here, but it is an instrument-rated meter for a 2-wire service. And then the 4S meter is the same equivalent form factor to the 2S, but just in the instrument-rated form. 5S, 45S, a 6S and 36S, 8S, and then the dual 8S and 9S, and then lastly our 9S. So I list a couple of the old mechanical induction forms on here that are really probably not very relevant any longer, but I list them on here for a specific reason that I'll go over. But these classes of meters here are all instrument rated. The 5S and the 45S are essentially the same form factor of meter, even though their numbers are different. And that came into existence because of the electronic meter. The same holds true for the 6S and the 36S. By the design of the electronic meter, the meter manufacturers needed a new form factor for the 5S, and they needed a new form factor for the 6S. And so they designated the 45S as the equivalent to the 5S, and the 36S as the equivalent to the 6S. These meters have the same base configuration, the same terminal configuration, so if you walked up to a mechanical Form 5S meter and needed to change that out to a 45S, there's nothing to do other than just exchange the meter. But they are distinctively different form factors. The 8S was the old mechanical meter for 4-wire deltas. And those were distinctively different meters than what we deal with today in the electronic meter. It was not really considered a 3-element meter like the 9S meter was, and so we don't see really any of those meters nowadays. But the 8S/9S, which is what we call the dual form electronic meter, is a true 3-element meter. It's applicable in the old 8S applications as well as the 9S. And so again, these are all instrument rated class meters. Most every utility has these in their population. And then lastly, this category is the equivalent to the previous category, but just in the self-contained category for Class 200 or Class 320 or even Class 400. So the 12S, the 12SE, the 12K, the 15S and 16S, and then the dual form 16, 15S for both Class 200 and Class 320, and then the K-base application. Again, these are equivalent to these previous numbers, just only in the self-contained. In terms of element configuration, the 12S meter and the 5S meter are both 2-element meters, so they measure in the same fashion, although one is capable of 200 amps relative to the other one being a 20 amp CT-rated meter. 16S, 15S meter is the equivalent to the 8S, 9S, just in the self-contained form. So all of these form factors really represent probably the most popular, more predominant form factors that are in anybody's utility system. Now, one of the things that I have observed along the way in instructing and kind of training, with just different individuals in the utility business, albeit it's mainly metering personnel, I've had the opportunity to do some training with line personnel, service personnel, which are not predominantly metering personnel. And there's something to be understood about being able to correlate form factors to transformer service configurations along with the phasing, whether it's single phase or 3-phase, and the number of wires. So this matrix here is the most common transformer service configurations that any utility would have. And it correlates to being either a single phase or a 3-phase application, the number of wires associated to that service, and then what the applicable form factors are for that particular application. So linemen understand transformer configurations. I would like to say that that's probably true for metering personnel too, but I have discovered on occasion where maybe a utility doesn't really cover that information in depth enough, and so a metering personnel would walk up to an installation, and while they may be familiar with the 9S meter, if they were to validate that to the transformer bank, they might have some difficulty. So this matrix will help tie those things together so that, for example, a 120-208Y. Well, we know that that's a three-phase installation. We know that's a 4-wire. And then these are the associated form factors that correlate to a 120-208Y. In contrast to that, a 120-240 Delta, it's still a 3-wire service, or 3-phase 4-wire service, and it also has those similar same form factors that correlate to that. So each one of these has multiple form factors, as you can see, except for a couple of those. And it's important to understand what meter forms correlate to the different service configurations. In addition to that, it's also very helpful to understand the association of class amperage of meters to whether it's single phase, 3-phase, what the associated meter form factors are, and then the number of terminals that are associated to the meter form as well as the class amp of meters. I've heard this so many times, I can't even count how many times, that a utility will say that their line personnel will call and say, hey, what service socket do I need? You know, how many terminals do I need for this type of service? Which tells me that they're not familiar enough with the number of terminals in a socket that would correlate to a transformer. So this matrix does that. It ties the class amp, which designates whether it's a self-contained or an instrument rated, whether it's 3-phase or single phase, the form factor or meter associated to it, and then what socket terminal configuration is associated to that class and that form factor or meter. So this is important for all the reasons I stated, but it's also highlighting the fact that you can install form factors in the wrong socket, which could be catastrophic. I mean, that turns into an immediate safety hazard that if someone's not familiar enough with the socket configurations and the form factors of meters. So again, the previous slide and this slide, one of the things I encourage people to do since I give this presentation out is print these out and laminate them. Put them in your vehicle, you know, so that you have quick reference to them out on the job site. That way, because you'll develop a memory for these things, but for a while you may need a laminated copy of this thing so that you can utilize it out in the field. Now, let's begin taking a look at some socket configurations. One of the things that I've observed over time with individuals that might be talking to each other and maybe they're not in the presence of one another, maybe they're on the phone or they're on the radio, and they're trying to talk about something relative to the socket configuration, and one individual is looking at the meter from the front side while the other individual may be looking at the meter from the back side. Well, that's a complete inverted situation. They're going to get themselves confused by not having some point of reference. So this slide here is taken directly out of the Landis+Gyr manual for the S4E manual. And the way you need to appreciate this slide is really from an orientation of the front side of the meter. So if you have a meter and you're holding it up in front of you, this is the elements as well as the terminal configurations from a frontal view. Now the next orientation is that you need to develop, and maybe utilities do this differently, but what I can tell you is for the most part, the industry looks at these types of schematics from left to right. So for example, if you were to look at this element, actually I'm going to use this drawing because it's a little lower. So if you look at this 16, 15, 14S meter, it's a 4-wire, 3-element meter. This element here would be considered element A or element 1. This element here would be element B or the middle element or element 2. And then the far right-hand element would be element 3 or element C. Or the right-hand element. Again, there's different ways that people reference this, But the key is having a proper uniform orientation and reference, whether it's left to right or right to left, and then a naming convention that your utility personnel will adopt. And it will really mitigate confusion when individuals are talking to one another and they're not in the presence of each other. So lastly, these represent several different form factors which we've already gone over. There's a couple in here that are unique. The Form 29 and the Form 56 are kind of unique to certain utilities. But the other thing I want you to pay attention to, and we've talked about this a little bit, but in regards to polarity in metering, polarity is important. That helps to designate the direction of current flow, and that designates the direction of power flow, whether it be delivered energy or whether it be received energy. So it's very important to take and make observation to polarity markings on schematics. So for example, you'll notice on the 16S meter for the current element, this black square indicator here on the current element is the polarity marking for the current element. Likewise, the voltage coil, if you will, next to it has the same polarity marking. So these two elements are in polarity with each other and have to be in order for this element to produce a forward torque. So for example, this meter's connected into the socket. The top side is what we would refer to as the line side. So power is obviously going to flow from the transformer down through the top side of the meter, which will result in a meter rotating forward. If for some reason this meter were bottom fed and it were not corrected, say in the meter program, so as to invert that in the metering elements, the power flow would be through the bottom, which is going to be the opposite side of the polarity markings, and that meter is going to rotate backwards. So polarity markings on any given meter farm are important to understand from a direction of current flow and power flow. This is just the second slide to that one that shows the K-base configurations as well as the 2-wire and the 3-wire meter. So operating amperages by class. So when we talk about class of meters, I mean, we often refer to that as class 200 or class 320, but we often don't think about, operating amperages, especially when it comes down to, well, how much current does it take to actually make that meter start running? Well, for example, a class 200 meter, which again is our most predominant meter, we know that most class 200 meters have a test amp of 30. If you're going to put that meter on a test board, you're going to put 30 amps on it and test the meter for accuracy. Obviously, the meter can handle a lot more than 30 amps, but it actually takes 50 milliamps of current for that meter to detect and begin measuring power. As a matter of fact, I had a customer call me here the other day, and they had some small RV pedestals that had lights in them for walkway lighting, and there hadn't been any RVs that had been installed or set there yet, so all they had were these lights, and they didn't understand why their meters weren't registering. Well, to come to find out, the meters didn't have enough starting current. They only had probably about 15 to 20 milliamps, and that meter required 50 milliamps in order to start measuring current. So every class designation, you'll notice, has a certain amount of starting amps, certain amount of continuous maximum amps over a 5-hour period, and then a temporary maximum 6-line cycle, which would represent like startup or inrush current, for a very large load over a very short cycle. So important information to just appreciate, but obviously we more associate to the actual class, for the service that it's going to be installed in. So continuing on with the manufacturer uniformity, so nameplate information is by far one of the most important things that we need to have really good familiarity with on meters relative to the application we're going to use. So number of wires, you're going to notice a wire designation on every nameplate, whether it's a 3-wire, a 4-wire, a 2-wire, but obviously that, this refers to the total number of wires in the circuit, including a neutral, if one exists, for which the meter was designed. For example, the Form 2S meter, it's a 3-wire meter. And the reason we designate that as a 3-wire meter is because we know a single-phase service is 2 voltages of 120 volts each, along with a phase-to-phase voltage of 240, because we know that transformer is center tapped. So obviously there's 2 legs of 120. There's a neutral conductor for return current carrying purposes, and that's designated as a 3-wire meter. Well, we have a 3-wire delta meter that is also a 3-wire, but it's a 3-phase meter. And we don't have a neutral reference conductor on a 3-wire delta because there is no neutral current carrying conductor in a 3-wire delta. We may have a corner grounded delta for the purpose of safety, but a 3-wire delta bank is typically known as a power bank for phase-to-phase motor load. But each of these nameplates would have a 3-wire designation on them. So voltage rating. Potential coil is designed to operate at a specific voltage rating, and these are levels that have some percentage, plus or minus. And it's very important to understand voltage ratings on meters. It really was very critical back in the days of mechanical meters because those meters were built for specific voltages. If you went to a 277-480 application and you took a Form 9S 120 volt meter, you're going to burn that meter up as soon as you install it because it's not rated for 277 volts. Now, we've done a good job of institutionalizing our workforce over the last 15 to 20 years with solid state meters that auto range. These meters are built with auto ranging voltage capabilities so that it can handle voltages from 120 volts all the way up to 480 volts. And that's been great, and that's been very handy, in terms of just convenience, so that you don't have to juggle a lot of different meters. But quite frankly, I think it has sort of introduced a little bit of a lackadaisic attitude, in not giving nameplate attention sometimes. And the reason that this is still very important is because in the residential class meters, those are voltage specific. You have to pay attention to the voltage rating on residential meters because they do not have voltage ranging potential elements in them. So I was raised up in the old mechanical world, of course, so we just were taught that you have to pay attention to voltage ratings, and so I like to adopt that that's still very important. One other reason is that you just need to know what voltage you're dealing with. It may have something to do with the protocol that your utility adheres to in terms of PPE equipment. Maybe your utility doesn't require a certain class of glove if it's a lower voltage as opposed to a higher voltage. Well, the only way you would know that is you got to make voltage measurements or at least the work order. Something's got to tell you what the voltage is, and you need to be able to correlate that back to the nameplate on the meter. So test amps, not going to spend much time on this. Obviously, we understand that meters are tested for accuracy. You just got to pay attention to the test amp rating on the nameplate of the meter in order to know what value of test amps to test the meter at. Class designation, again, we've talked about this quite a bit now, but it's it's the maximum load that the meter can handle. Not going to really walk through all of this, but ANSI does have standards around how class designations are established, relative to test amp, correlated to the class amp rating of the meter. So you can review this as you wish, but class amps, to me, it's pretty much as important as the voltage. I mean, you got to know that you got to have the right class of meter. So type designation. So type designation is a unique variable to the manufacturer. Every manufacturer will engineer and produce a product that they're going to give some sort of designation, or name convention to the product. For example, the Landis+Gyr family of meters, they have had several different product types over the years, everything from the old mechanical MX meter to the Focus AL meter to the Focus AX meter, Focus AXE service disconnect, the S4E meter, and now the S4X meter. These are all examples of type designations. And then they have their newest meter, the Revelo meter, that is in design and development, which will be released probably next year. So you'll notice a type designation on the nameplate, which is important because utilities that adopt technology come to use that type designation as a reference. And then lastly, form designation. ANSI really established a consistent standard around form designation years ago for the purpose of reference to the type of meter that needed to be in the proper service. So we're going to go over some of these from a visual perspective here shortly, which is actually the next slide. So several slides here of photographs that we'll use to talk about. Obviously, this is a Landis+Gyr meter. It's an AX S4 type meter, but you'll notice that there's all of this other nameplate information that we've talked about. So basically we need to be able to determine, okay, was this a self-contained meter or is this a CT rated meter? Obviously the associated form factors to self-contained and transformer rated are listed there. And we can see that this meter is a CT rated form 45S meter. You'll notice that it states 45S within parentheses 5S. And that was to help the industry that understood the 5S meter from the old mechanical days, and that this meter was a compatible replacement to the old 5S meter. Obviously, it tells us it's a class 20 device. This is an auto ranging voltage device, 120 volt to 480 volt. Test amps of 2.5. The KH of the meter, talked about that. How many watt hours is represented in the equivalent disk revolution? Number of wires. We see that this is a 3-wire meter. And also the frequency, which obviously we would take for granted here in the US since everything is 60 hertz. And then the manufacturer serial number, which is a requirement of ANSI for the manufacturer to apply a manufacturer serial number. And then there's a few other things here that Landis has included on their nameplate, like the voltage transformer ratio, the current transformer ratio, a location for putting the multiplier factor for the meter if that's required. And then lastly, this was a utilities meter that used their own custom serial number, which you can see a badge up here at the top that's got their own unique number. That's not an ANSI requirement, but a lot of utilities still use a company number or a customer serial number as opposed to using that number, although that number might be a number they also reference. But many utilities have began to adopt just using the manufacturer serial number. One of the reasons that's true is that with AMI communications, the COM module that is inside the meter is married to that number. And so when you get test data from the manufacturer, their test data is going to reference that COM module number as well as the serial number of the meter. And those two devices are married together in the data file. I just put an old nameplate up here of an old 8S meter to kind of illustrate that back in the old days, nameplates were actually stamped with information, you know, so they would build up a bunch of blank nameplates, and then based on the catalog number of a given meter, they would stamp in the relative information that was correlated to that catalog number for that meter. This is an old GE Form 8S VM66S meter that was used for a 4-wire 240 volt delta service. So we're going to look at some base configurations now. So the Form 4S meter. So we often refer to as the Form 4S meter as a 6-terminal meter. And clearly that's an accurate depiction of the meter because the meter actually has 4 terminals. Now obviously we're looking at the back side of the meter as opposed to the slides that we looked at earlier that were the schematics, and we were looking at them from a frontal view. There is nothing wrong with looking at meters from the backside from an element perspective. You just have to maintain the orientation, because obviously from the frontal view that we were looking at earlier, everything is just, you know, inverted or just the opposite side, you know, when you look at it from the back. But obviously with all meters, we know that we can recognize terminal, most of the time, terminal current blades, just obviously because the blade is the larger of the other blades' associated potential. Now that's not always true, and I'll have an example of that momentarily. But you'll also notice that in the 4S meter that the potential elements are horizontal as opposed to vertical on the base plate. So it's important to develop that familiarity in the terminal configuration to the form factor, so that if somebody says form 4S meter to you, there's several things you immediately know. Oh, that's a single phase CT rated meter, 3-wire. That's a 6-terminal base. That has a single potential coil. That has 2 current elements. I mean, I just probably rattled off about a half a dozen different things that correlate to the term form 4S meter. And that's what I really am trying to illustrate when you're building a vocabulary and association of things in your mind. That's an example of that. The Form 1516S self-contained meter, we often refer to this as the 7-terminal meter. It's installed in a 7-terminal self-contained socket. Obviously it has current elements as well as potential elements. I listed the high leg here just as an example when it's plugged into a 4-wire delta, because traditionally speaking, the old 15S meter, you had to have the high leg on the right-hand side because that was the 208 rated element. And if you didn't have that on the proper side, the meter was not going to meter correctly. So I just listed that here. This is denoted as the 7th terminal. And it looks a little different than the other terminals. It's actually a little smaller, and it's specifically positioned in the base of the meter so that it lines up with the bayonet in the 7-terminal base, and that is its point of reference for all voltages. Very often I've had people call and say, hey, I have plugged in 3 brand new 16S meters and none of those meters will light up. There's something wrong with your meter. And the first thing that I'll ask them is, did you validate that the 7th terminal is in the proper position and has good integrity? And many times they'll come back to me and say, well, no, it wasn't lined up properly, and so this blade wasn't stabbed in. It might have been offset to the side. Or maybe the neutral connection inside of the socket was jeopardized in terms of integrity and it wasn't providing an adequate neutral reference. You got to remember these meters are powered up, by a specific phase, and that phase that powers that meter is not only intended to be used with the potential coil, but it also runs the power supply. And if you don't have proper voltages, the meter, it's not going to light up the display of the meter. So remember that on this meter, that the 7th terminal is very important to that. So the 12S meter, we often refer to these as 5-terminal bases. We have 5 different terminals that you can see here, and obviously the designation of 1 and 2 would be for the element of current, and this would be the other current element. But I want to show you something here that's really important. You'll notice that the 5th terminal is in what we would refer to as the 9 o'clock position. Now, utilities most often will adopt a position for the 12S meter, whether it be 9 o'clock or whether it be 6 o'clock. And that's because the sockets can be equipped, for the 5th terminal to be located at one of those 2 locations. I'm not going to try to defend one over the other. I see them in both cases, at different utilities. But one thing that you'll notice is that you can have an offset right here. You'll notice how this is notched out, on both sides of the hole. And basically, when catalog numbers are built for Form 12S meters, you can specify that if it's a 6 o'clock position, it can either be 6 o'clock offset or not. And you have to pay attention to that for the exact same reason that the previous slide, because if you don't have a good point of reference, which that's what that is, that meter will not energize properly. So you got to pay attention to that. 5th terminal, of course. Obviously the other location. So the 5S meter we often refer to as the 8-terminal meter. Clearly we have 4 blades on the bottom, 4 blades on the top. 8-terminal base has to be used with this. This is the meter that you have to pay attention to just acknowledge that these blades here are the exact same dimensions as the current elements on the outside of each side of the meter. But these are potential, these are voltage elements, as is this one. This is what we would call the reference to the corner ground of the delta. But these are the same size, just to be clear, and that is really the only meter that I'm aware of that has that type of configuration. But it is an 8-terminal meter, 2 elements, obviously 2 voltages and 2 currents. The 6S or 36S, this is our 13-terminal base, which is the same base as a 9S, but they are distinctively different in one very specific aspect. The 6S meter has one less potential coil than what the 9S meter does. So for example, we'll notice the current terminals on the top and the bottom, and then the row of smaller blades across the middle, which basically we have a voltage A potential here and a voltage C potential for the 6S meter here. There is no connection to this terminal here. And then obviously the neutral connection is down here. Very similar to the other things that I brought up about integrity of neutrals. I've had people call me and say, hey, I've stabbed in 2 or 3 6S meters and none of them will energize. A lot of times that integrity of the neutral connection is in question. So you got to pay attention to that. The 9S, it's practically the same configuration because it is a 13-terminal configuration, but the only difference is this is not voltage C, this is voltage B, and then voltage C lines up on this 3rd terminal. Everything else about the meter is the same. The current element configurations are the same, the neutral's in the same position, but as you can see, I could take this meter and go up to a 6S socket. It's still a 13-terminal socket, and I could stab this meter in that socket and we would not be registering energy properly. So that is a common mistake that can be made for utilities that are still using 6S and 9S meters. And then lastly, this is just the K-base meter. Many people don't use the K-base, so it looks foreign to them, but it's a very heavy bar configuration that's bolted in. Obviously, you can see the holes in the bus bars, and then the neutral reference connection. Basically, if this meter were looking from a side view, that it may be that deep, that has the housing for the current assembly. It's basically a CT-rated meter that's really established as a self-contained K-base meter, but there are current transformers built into the base that handle the currents up to 400 amps. Again, a little bit about polarity markings. Obviously, any given meter will have current blades, for the metering current elements, as well as the potential elements or VTs. We don't typically refer to them as VTs, but you'll notice the current element and potential element polarity markings again. Any disconnect link or potential link that may be on a self-contained meter. Line side typically is always to the top of the meter versus load side. So polarity is very important again, and just being able to identify a current element versus a potential element. You'll notice that the current elements are always usually more heavily bold versus the potential elements that are a little bit thinner line, to depict a actual potential element. Again, this is just a 2S meter, but we could have any form of meter up here. This is a form 9S, obviously again. Now the one thing I didn't mention on the previous slides there, in the 13-terminal base, it used to be fairly common that we could have KYZ connections to these 3 blades here that were required for an installation that was providing energy pulses to a SCADA system or a demand-side load management system. That's really not very common any longer. As a matter of fact, there's some of the meter manufacturers that they don't even build the meter anymore that would provide that. You have to have an internal card with a cable that comes out of the base of the meter that then would be connected. But it was common back in the old days that these three blades here would have KYZ pulses. Again, current element A, current voltage element B, and then lastly, current and voltage element on C phase. And if this were in a 4-wire delta, this would be what we refer to as the wild leg, or the freak leg, or the red leg, lots of different terms for it. But this potential element in a 4-wire delta has 208 volts on it versus these that have 120 on it. So if you have the wild leg of the meter in the wrong place, in other words, if that one was connected over here on the 208, the solid state meter will measure that correctly, but it's going to give you a phase error, because when that meter it gets energized, it's looking for voltages in a very specific location from a terminal perspective. And when it sees that there's not 208 volts on this leg and it's over here, it's going to flag a phase error, just alerting you to that fact. Now, fortunately for us, the dual form meter allows for it to measure energy properly, but if you don't want the display of the meter flagging you with a phase error, you're going to probably have to consider moving that phase or either disabling that phase error. So that brings us to the end. We covered a lot of information here in these 70 some odd slides, and as the title of the presentation indicated, this is the fundamentals of principles of electricity metering. This was just intended to really lay the groundwork around fundamentals. Obviously, the craft of metering is a lot deeper than what we got into, and I would just have to encourage you that it's a long journey to develop the skills to be a proficient metering professional. But I can tell you, after nearly 40 years of being in the business, it's been a really rewarding craft. I tell people all the time, I didn't pick it, it picked me. But I've been really blessed to have the opportunity to be in the metering craft, and have made a lot of friends and met a lot of good people, and it's been a very interesting career, and hoping that this has been a good training for you, and look forward to the next time that we can get together for some future training. Farewell to everybody. Safe travels.